Hi there. So I just want to make this video to discuss about spinning tree, specifically the 802.1D. That's sort of like the foundation of spinning tree understanding. So I want to start here. Now, forewarning, the video it's going to be long, and a lot of it is me talking um, with the configurations of the COIs. I'm trying to approach these conversations with the configurations point of view. It's going to be a raw, long, unedited video. So just FYI, if you looking for something more high professional edited video, this is not this is not the video for it. So anyway, let's get into the spanning tree 802.1D. So we need to understand the what, the why, and the how of the of spanning tree. That should give us a good understanding of what we're gonna start with. So spanning tree is the short answer to that is it's a mechanism to prevent layer two network loops, and and that's involved with when you have redundant links within the network. If you look at the my lab here, right, you can see these switches are interconnected with multiple links to one another's, and this is for redundancy reasons. And so with redundancy, especially as a layer two, you need a mechanism to prevent the loops, layer two loops. And so spanning tree is what the big uh, factor here. And so why do we use it, or why do we need it? So we definitely don't want layer two loops within our network. It will cause major outages. So that's the why. That's we don't we want to learn spanning tree so we can configure it to avoid spanning tree loops, right? Layer two loops. And how does it work? Well, the how, it's definitely gonna be explained, or it's better to discuss the how with the labs I set up here that you see on the screen. So let's get into that. Uh, Before that, let me touch on a little bit about the fundamentals, some of the terminologies you're gonna run across, or you'll be reading or hear about when it comes to spanning tree. So, all right. So the focus of this video, we're gonna talk about the elections process, the port rows state of the interface when it comes to spanning trees that participates in the spanning tree, and then the convergence, fine tuning, the performance optimizations of spanning tree. All right, this first thing here, you're gonna hear there's a lot when you reading about spanning tree or trying to understand about spanning tree. So this terminology is a the PBDU stands for Bridge Protocol Data Unit. Think of it's a language between the switches, right? Is the switches is gonna be it's gonna have the switches, they are gonna communicate to one another when it comes to spanning tree. And so and PBDU is a language of that communication, right? Think of it's like a letter. It's just gonna send to one another, and inside that letters is have a bunch of parameters that would tell the other switches, right? What's the status of each other, and also you can think of it. It's also like a heartbeat between the switches to know if, hey, is the upstream switch still alive, the downstream switch still alive, things of that nature, so that it knows when to update, right, a certain attributes to make span and tree constantly working to prevent loops. So PBDU, just remember that it's very critical components of span and tree. It is the language of span and tree protocol between the switches. All right, so the way span and tree works, one of the first thing is that it's gonna try to elect the root bridge, like the brain of the span tree operations, a centralized point of communications for all the switches, right? You can think of it that way. So the elections is a critical point to understand, and all it is it's just a comparisons between the switches. Who has the lowest BID or bridge ID, right? And so every switch will has its own bridge ID, and so they're gonna look at the neighbors and then compare itself to that bridge ID. If it's higher or lower, right? If it's lower, I'm gonna win the election. If it's higher, the other guy will win the election. So lower bridge ID is the winner. So inside that bridge ID, you have two components that's critical. You have the 16 bits priority and the 48 bits MAC address. First, it's going to use the bit priority for the bit ID to compare who has the lowest will win. If the bit priority is the same, the tiebreaker is going to use the local MAC address of that switch to compare one another. Now, there's some rules with the priority increase and decrease. So you can fine tune this priority number and to configure which switch you want to win the election. So you can do that. But every time you do an increase or decrease of this default value, 32,768, you have to do by 4,096 value increments or decrease, right? Increments or increase or decrease. So that's just a rule, right, of the priority values. Now, obviously, there's an explanation for that, which you can look into that. It's not hard to understand. Anyway, so again, the priority field also breaks into kind of two components as well. You have the extended ID, which is the VLAN ID, and then you have the bridge priorities that you can change, right? All right, so that's kind of sums up to what the root bridge election process dependencies, right? But BID or bridge IDs, whichever switch has the lowest win the election. And then we're going to talk about the port rows and states. So once you have span and tree elections process completed, you have the call a root bridge, and then the port states and row is start to be calculated, right, between the switches. So the root port is a single port on a non-root switch. So any switches that not the root switch will have this port rows. One of them, one interface will be dedicated for that row, right? It's called root port. And we can go to the labs and do some exercise to see how the calculation works for the port to be elected as a root port. So then you also have a designated port. So this is the port that's not the root port. So this port can be on the non-root switch, and all of it, all the root port, I'm sorry, all the root bridge ports is or are designated port. Okay, so designated port is essentially it's responsible for one, it could forward traffics, and it's also relay the PBDU language between the switches to one another, right? So this port functions is mainly for forwarding traffics, right? And then you have blocking port, which is that's what it's stand for, right? Blocked all data traffics. It's not going to send any traffic. However, it's still listening and receive PBDUs from other switches, right? From the neighbors. So the port rows, three of them, the root port, designated port, blocking port. So kind of remember the kind of functionality of these ports. So then we talk about the convergent timers. Convergent timer is essentially when the spanning tree needs to take some time to do the calculations so that it makes sure that the results of that calculations will be able to prevent layer 2 loops, right? And all it's doing is calculate the interface, the port state of the switch. And so the state of the port, right, is different than the rows, right? The states is different. So you have a blocking state, again, it's not sending and receiving data traffic, but still listening to PBDU. Listening state, so this is the first timer. For this spanning tree AO2.1D, it requires 15-second wait time for the state of that interface. Going from blocking to listening, that's 15 seconds. So this state, no data traffic is passing through. It only processes PBDUs to determine the network convergent. Once the 15-second wait time is over, it moves from listening to learning state. Here you have another 15-second wait time. Again, it still discards data traffic, but they start to populate the MAC address of the end device, right, or the switch, whatever that is. So then after that 15-second wait time in the learning state, it moves to the forwarding state. So here is when the spanning tree has converged. It calculates and it's put the interfaces of the switch in a way that is all agreed that there's no loops at this point, and it forwards traffic, right? Forwarding traffic. So this is a state where the network topology all agree and comfortable that there's no layer 2 loops happening. We'll talk about total delay, max age, a little bit more later. But again, by default, if you go from blocking state, right, with usually the state of a redundancy link, for that link to go to forwarding state, you'll be looking at 30 seconds of delays for all the calculations, spanning tree calculations in this version of spanning tree AO2.1D. Okay. So there's a way you can make that shorter, that convergent timer, with some of the Cisco features here, right? You have port fast. Essentially, a port doesn't need to be in the waiting state, blocking, waiting, listening and learning waiting state. It just go from blocking to forward. Now, special case is that you configure this port fast features on the interface that facing the, like a PC, right? Anything that's not running spanning tree on the other side. So edge devices, right? Uplink fast, it's another features that if a switch is connected to another switch, and that switch is considered a leaf switch, meaning leaf switch is a switch that at the leaf, right, at the far end, there's no other switches connected to that leaf switch. That's what we call leaf. So we know that there's no spanning tree need to runs on any other port beside the port that connecting back to another switch. And if there's a redundant link for that connections, that redundant link will automatically fail over to be a root port, right? So skip the 30-second delay, and we can demonstrate that in the labs. Backbone fast. Now, this is a little bit confusing to understand, but think of this as more I'll have to do, of it had to do with the indirect link failures. Indirect link failures is referencing the connections of an upstream switch that not the local switch that lost the communication to the root ports, the root switch. Okay, so and when that happens, you have features that you could bypass another additional 20 seconds of waiting for PDU to time out. And we'll go into that a little bit with the lab, right? Root guard is essentially a security feature to make sure that you know which switch is connecting to the root bridge, which interface connect to root bridge. You want to secure that port to be the root port and none other port to take that role. So you can enable these features that allows that to happen. Okay. All right. So that's real quick on the fundamentals here. Again, quick sum up again, right? PBDU's critical understanding of it is that it is a language, right? A communication ladder between the switches in the network for spanning tree. Root bridge selection, this process is critical because it's sort of a start of a spanning tree process, operations. And then the port row and the state of the interfaces. And then convergent timers for this 802.1d protocol. And then how do you kind of enhance the convergence timers with these features: port fast, uplink fast, backbone fast, and root guard. All right. So let's talk about spanning tree operations through the labs and through the COI's point of view. So what you see here, let me quickly talk about the setup here. So I use 4 switches interconnect with redundancy between them. Again, spanning tree care a lot about redundancy connections in the networks. So then I have PC connecting to these switches just so we can demonstrate some features, that convergence features that I mentioned earlier, specifically the port fast configurations. And so that's how it looked like. The switches, I already pre-configure a few things. Number 1, trunk encapsulation, trunk links between the switches. So all these links interconnect between the switches here are all trunks. And then VLANs. I configure a few VLANs already. So VLAN 1 is a default, and then VLAN 10 to 40, 10, 20, 40 I'll configure on these switches. Okay. So let's talk about the operations of the spanning tree 802.1d. So after you interconnected all these links that you see in this lab, right? Spanning tree, it's gonna start to the span tree. It's gonna begin, right? It's gonna kickstart that spanning tree. So PWU is sending between these switches, right? Inside that PWU, it's gonna look for the bit ID to do the root bridge elections, right? So out of all four switches here, one of the switch will be elected as the root bridge, right? It could be 1, it could be 2, 3, 4, whatever. It depends on the bit ID. Whichever switch has the lowest bit ID is going to win that root bridge elections. So we can look at the command line and see why, right? Why one switch is the root bridge versus the other switches, right? So I label switch 1 here as a root bridge, but we don't know. But let's find out why. All right, so what you need to do is this show command is really good. So real quick, right? I'm using Cisco iOS here. So I'm going to do show span the tree VLAN 1. Now, Cisco can run PVSD Plus, which is basically AO2.1D, but Cisco versions that modifies to that you can have span and tree per VLANs rather than just all VLANs. Right. So I'm just going to use VLAN 1 or VLAN 10, right? Because let's do VLAN 1. All right, so let's hit that. And I want to run that command to all four switches, because this command is going to show you why certain switch is elected to be span and tree root bridge versus other switches. So we'll do the same command for all four switches. All right, so we have the output here. Okay, so this output here, what you want to do is pay attention to this part of the output. This is basically the informations of that bit ID for this local switch. Okay, the bottom here. Okay, so as mentioned in that PowerPoint slides, right? The bit ID consists of the priority value and the MAC address. Okay, so this local switch here has the priority value of 3276. I'm sorry, 32769. The default is 32768 plus the VLAN. Okay, that's why it's 32769. And this is the MAC address of this switch. So we go to switch 2. We have the priority and then the MAC address of switch 2. Same with 3 and 4. So if you notice, what you've already noticed is that the priority value is the same for all four switches, right? 32769, 32769, 32769. Okay, so because of the priority values is the same, then the tiebreaker is going to be the MAC address of that switch, which whoever has the lower MAC address of this in the tiebreaker will win the root bridge election. Okay, so because the priority is the same, we can move on to looking at the MAC address to see which of the four switch has the lowest. So this is the MAC address. All right. So I'm paying attention to the last four hexadecimal there. So you have 1,000, 2,000 on switch 2, 3,000 on switch 3, 4,000 on switch 4. All right, so I can conclude that switch 1 has the lowest MAC address. So switch 1 won the root bridge elections, right? Based on that rule set in standard spanner tree. So then you want to look at the top output here. It's saying that you kind of tell you that this switch 1 is the root, okay? And it listed the information of the root bridge bit ID here. And it's identical to this switch. So this validates that switch 1 is the root bridge, okay? If I go to switch 2, and if you look at the top part here, it listed the information of switch 1 bit ID, okay? So this switch 2 agreed that switch 1 is the root bridge. So it's listed switch 1 is bit ID here. Same with 3 and 4. So the election, it's over, right? All four switches agree that switch 1 is the brain of the spanner tree operation, is the root bridge, right? So that is very straightforward, right? We care about the bit ID. Whichever has the lowest, whether it's a priority or the MAC address. Well, you look at the priority first if all equal, and then you look at the MAC address. Okay. All right. So straightforward. So let's do a few exercise to help with that understanding a little bit. So what if I do this? What if I want, let's move this out a second. What if I want switch 4 to be the root bridge instead of switch 1? How do I do that? Okay, so let's think about that for a moment. We know the root bridge elections depends on the bridge ID of the switch. Whichever switch has the lowest wins. So if we want to move the root bridge to switch 4, then we have to make sure switch 4 has the lowest bit, right? All right, so with that, let's look at the information again. So we know that the priority of all four switches is the same. Switch 4 to 3 2 lost the election to 1 is because of its MAC address, right? So the MAC address more likely is not the thing you want to adjust, right? So we don't want the MAC address to be adjusted. So we don't essentially, I'm saying don't adjust its MAC address on switch 4 to make it has the lowest so that it wins the elections. Better way to do is to adjust the bridge priority value. Again, it looks at the priority first and then the MAC address, okay? So let's play around with the priority value, right? So in order for me to make switch 4 the root bridge, I'm going to change this priority value to the lowest of all 4 switches so that it wins that root bridge elections. So here is the command to do that. And there's a few ways to do it, right? So you do spanning tree, whatever VLAN you want it to be, the root bridge, again. Cisco run PVST plus, so you can do per VLAN or all VLAN. Let's just do all VLAN. Let's do question mark. All right, so spanning tree VLAN 4001 to 4094. What do you want to do with that? Well, you can change the priority menu with this command here, right? But let's do this one. It's easier, right? So root, we want is a root bridge. So you want to do root primary. So you could do this one. The system will calculate it automatically for you to lower the priority. There's a default value, like 24,768, right? Or you can do it manually with this, right? And then whatever you do with it. So let's do this first, right? Let's do this and see what happens. So this commands our intention is to promote switch 4 to be root bridge. So this command we want to enter to switch 4. All right. So once we've done that, let's do a show command to see what happened. And you can see the priority of this switch 4 switch now changed to 24,576. Yeah, 24,576 is the value of this commands to lower the priority to. Okay. MAC address stay the same, but the priority value changed. And on top, you can see that it is now the root bridge, and it has its own information here. Now you go to switch 3. This was previous before. You do the same spanning tree command. Now it's updated to switch 4, right, as the root bridge. Same with 2. Right. It agree and accepted switch 4 as the root bridge. Now spanning tree for VLAN 1 on switch 1. This one was the root. Okay, so let's see what happened. All right, so it's no longer the root bridge. It agreed and accepted switch 4 as the root bridge. Okay, because of this priority on switch 4 that is the lowest out of all 4 switches. Okay, so that's how you want to configure your switch, your network environment with the root bridge. The reason you do this and don't want to leave it by default is that you know maybe so the reason you want a switch to be a root bridge is you want that switch to be the most powerful in terms of, you know, high-end compute, more memories, whatever, right? You want that switch to be the most stable, most powerful switch in your network to be the root bridge, because so you can say all traffic could go across that switch, right? So again, let me go back to, there's another way to promote a switch to the root, right? And this is obviously the simplest way because you don't have to remember the value, right? But if you want to do it this way, you can do it as well, right? So on switch 4, we do VLAN 1 to 94 and priority value. Now here, if I do a question mark, you have to know a value that's in the increments of 4096 or decrease it by 4096, right? So I don't, on top of my head, I have to think about calculations or whatever, right? But you can just simply do this, right? Which is gonna accept it. So you do this, you change the priority value manually instead of do the root primary, and then we'll see what happens. Okay, so you can see, yeah, it took that priority and set it manually to what that value you added. So doing this again will make this switch has the lowest priority, and so it's still going to be the root bridge. Okay. All right. So let me remove that to see what happened. Okay. So one thing to notice here, again, you added this command root primary, right? Which lower the switch to 24,576 plus 1 for VLAN ID. Then you manually configure this value. Essentially, it's replace this completely, like it deletes out of the configurations, and then it set that value to 4096. Now you would assume if I remove this command, then it will still use this command root primary, but that's no longer the case, because once I remove it and I do the show VLAN again, it fell back to the default value, right? Yeah. Okay. All right. So let's put that back. Okay. Okay. All right. So now this guy is still root bridge. All right. Next step, what we want to do is we want to use we want a scenario to have a network topology to have a secondary root bridge. So this will help you with the election process that doesn't need to reruns. So your convergency in the network, it's better to have another switch dedicated to be a root bridge as soon as the primary root bridge fail, right? So this is a very good use case and recommended to do here. So you don't have to run so the spanning tree process won't run in the background when the primary root bridge fail. So let's do this. So how do you do this? Again, I want switch 3 to be a secondary root bridge. Switch 4 to be still a primary root bridge, right? So again, it's going to have to do with the priority value. So what happened here is think about it, if you want switch 3 to be a secondary root bridge, in terms of the priority value that you need to set, you have to think that it has to be higher than the switch 4 as a primary root bridge, right? It has to be higher, right? But at the same time, it needs to be lower than the rest of the switch in the network, okay? So again, a quick, easy way to do this is do span tree VLAN 149 4094 root secondary. I'm sorry, I'm on switch 4. You want to do this on switch 3. All right. So what happened after you do that? You can see this switch. It was using the default value before we enter this command. Once you enter that command, you can see the values now, right, lower, 28,672. This value is still higher than the primary root bridge, which is switch 4, but it is higher than switch 2 and switch 1, which makes switch 3 the secondary root bridge. Okay, so I think with that, it should cover the understanding and how to manually configure your root bridge in the environment, in your network environment. Okay. Next video, we'll look at the port rows and state once this root bridge election process is completed. All right. See you in the next video.